Welcome back everyone. In the last lecture we were successful in finding out the operator that related the output and the input, and we called it the transfer function. The only condition that we kept was the initial conditions are all 0. When the initial conditions are all 0, the inputs and the outputs were related by the transfer function of the system, and we got a nice algebraic equation. It was just a multiplication. The transfer function multiplied by the input gave us the output. Let us move forward from that point and solve some examples today to see how does that help us in finding out the response of the system. So first of all, this is what we started with. We wanted this operator. I wrote H, now I have replaced it with GT, and the reason will be clear soon. Now if I take Laplace transform of this, I will get US, YS, and the Laplace transform of GT is GS. That is why I replace H with G now to make it convenient. Okay, and you see YS is equal to GS into US. I am telling you again that we have assumed that all initial conditions are 0 when finding out the transfer function. Now, if I see, I know that Ys is nothing but Gs into Us. Now, if I do a Laplace inverse on these on both sides, what is the Laplace inverse of Ys? Yt. What is the Laplace inverse of multiplication of two Laplace transform? The convolution of these two, right? So, in the time domain, the output is nothing but the convolution of this Gt and Ut. Okay, and this Gt has a name, special name. Gs is called transfer function. Gt is called impulse response of the system. Okay, remember the name because I will be using this word quite often. The impulse response of the system is Gt, and the Laplace transform of the impulse response of a system is the transfer function of that system. Impulse function has lot of physical interpretations as well. Again, I am not going to delve into those. Those are covered in signals and systems courses, and you can go through any book on signals and systems, you will know about them. What is important for us is that we have been successful in finding out an algebraic relation between the input and output with the help of the transfer function. Let us take examples to see what are the informations that can be taken out from the transfer function. First of all, the question is find the impulse response of the system with transfer function Gs. So, the simple question, it's a very simple question. What is the impulse response of the system if the transfer function of the system is the Gs? And we know that what is the relationship between transfer function and impulse response? The Laplace inverse of Gs is nothing but the impulse response. So, I have to find out the Laplace inverse of this. So, how do we find out the Laplace inverse of this? To find out the Laplace inverse of this, we will simply go for a partial fraction method where we will take the partial fraction of this. So, this can be written in this way. So, how do I find out the value of A1? So, A1 can be found out by S multiplied by GS, evaluate S equal to 0. I hope all of you know how to find out partial fractions. This is part of maths, basic maths courses. So, you find out the partial fraction with this method, and these are the coefficients A1, A2, A3 coefficients that you get. So, the partial fraction is this. Now, why are we finding out the partial fraction? Because once we find out the partial fraction, you just have to do a Laplace inverse on these terms and see, like Laplace, if I have to do Laplace inverse of this, Laplace inverse can be distributed over this because Laplace inverse also will satisfy superposition. So, now Laplace inverse, see Laplace inverse of 2 by S minus Laplace inverse of 5 by 2 by S plus 1, then you have plus half of, or Laplace inverse of half of S plus 3. But what is Laplace inverse of 2 by S? 2 times, because the Laplace inverse of 1 by S is use step input or step signal. Laplace inverse of 1 by S, and 2 is a constant, so I can take it out. So, 2 times 1 by S is 2 u step. Similarly, 5 by 2 I can take out, I took out 5 by 2, and what is the Laplace inverse of 1 by S plus 1? This is nothing but e to the power of minus t u step, right? Because what was the Laplace of e to the power of a t u step? This was nothing but 1 by s minus a, right? So, I am just using the reverse way because I am finding out Laplace inverse. Again for Laplace inverse of half divided by s plus 3, half I can take out. So, this becomes half of e to the power of minus 3t u step. Okay. So, finally, the Laplace inverse or the impulse response of this system, Laplace inverse of the transfer function is this, and this is the impulse response of the system. Okay. So, now let us move to the next problem, which says what is the step response of a system with transfer function this. Now, what is the meaning of step response of a system? Again remember, response of a system means the generally, unless otherwise mentioned, response of a system means output of the system. And here we are saying step response of a system, that means the input of the system is a unit step input. So, if the input of the system is a unit step input, what is the output of the system? That is the question. But that is also, we can find out that also, right. So, we know Ys equal to Gs into Us. Now, if ut is unit step, we know what is Us. Us is 1 by s, right. The Laplace transform of unit step is 1 by s. So, which means that y of s is nothing but Gs is s plus 6 by this is the transfer function Gs multiplied by Us. Us is 1 by s. So, you have this, and then again for this also you can find out the partial fraction. You can find out the partial fraction for this. You go ahead and find out the partial fraction. So, the partial fraction, I mean, I am just listing out the method. The method, I hope all of you know the method. If you do not know, you can go up and look into a mathematics book where you will find out the method for partial fraction. But I have listed down the method by which you can find out the partial fraction. But I am not going to, of course, spell it out, because I mean I am hoping that all of you know how to find out partial fractions. As a whole, the partial fraction of Ys comes out to be this. Now, we will try to find out the Laplace inverse of this. So, what will be the Laplace inverse of this? Laplace inverse of this means the Laplace inverse of these three terms. Again, we can separately write these terms. So, here this can be written as 2 by s square. Then we have minus 7 by 3 s by s square, which is minus 7 by 3 by s. Then we have 5 by 2 by s plus 1, and then minus 1 by 6 by s plus 3. So, now again for each of these term I can find out Laplace transform, Laplace inverse. Laplace inverse of 2 by s square is 2t, because the Laplace of t is 1 by s square. I know that. So, then what will be this? This will be 2t, right. So, that is how I found out. So, and then Laplace inverse of 7 by 3 by s is 7 by 3 u step. 5 by 2 by s plus 1 is 5 by 2 e to the power minus t, 1 by 6 e to the power minus 3t, and so we have the step response of the system. So, you see, with the help of the transfer function, I could find out the impulse response of the system. I could also find out the step response of the system. In a similar way, you can also find out the ramp response and the different types of, if in this case I have given ut to be equal to u step. Ut can be some other function also. You can find out what if ut is sine of omega t or sine of 2t, say sine of 2t. How do I find out? Same method, only us will be changed to 2 by s square plus omega square, then 2 by s square plus 4 in that case, and then you repeat the same procedure. So, for different inputs you can now find out the output of the system using Laplace inverse. Now, there is one property that will be very important for us in this course, and that is why I list down that property of LTI system, and that property is called what will happen to an LTI system if the input is 0. So, let S be an LTI system. If the input to the system S is 0 for all t, then the output of the system S is 0 for all t. There is a caveat here, provided all initial conditions are 0. Okay. If the initial conditions in the system are 0, what can be an initial condition in the system 0 mean? Suppose you have an RLC circuit, and RLC circuit is a LTI system. Okay. Suppose you have an RLC circuit, resistor, inductor and capacitor. So, suppose in that RLC circuit the capacitor is initially charged to some value. So, in that case we will say that, okay, and you started the experiment just now, but the capacitor was initially charged itself. So, in that case we will say that the capacitor is initially charged to some value. Okay. So, when we find out transfer function of a system, we assume that there is this no charging, there is no extra information from the previous time instant. So, we are starting at this point afresh, everything is at 0 and then we are starting. Okay. So, in this case also, if an LTI system which is starting, whose all initial conditions are 0, is subjected to a 0 input, then the output will always be 0. This is a necessary condition. That means, so if the input is 0, the output must be 0. Okay? Let us see why. Okay? Why is this true? So, suppose to the contrary, I assume that when I give input 0, the output is some other value other than 0. A of t is there, which is not 0. Okay? And then say h of ut is equal to yt. That means the output of the system is yt when the input is ut for some other input. Since S is an LTI system, we know that h acting on alpha ut must be alpha times of h of ut. This we know because this is an LTI system. So, then what can we write? You see, suppose h of alpha ut, suppose alpha is 0. So, if alpha is 0, then h of 0 ut is h of 0, because 0 multiplied by any function is 0, but h of 0 is at, right. So, this is equation 1. There is another way of writing this same thing. H of alpha t, this alpha I can take out, right. I took out alpha, h of ut, but alpha is 0, right, 0, h of ut is at, 0 into at is 0. Both these equations are correct. So, which means that this and this must be equal, right. Now, if this and this must be equal, then what happens? Then there is a contradiction, because we started with the assumption that at is not 0 at all time. So, since we have reached a contradiction, our first assumption itself was invalid. This is called proof by contradiction. So, we have proved that if the input to the system S is 0, then the output to the system must be 0, provided initial conditions are 0. Okay. Now, then I ask you the question, are the systems given linear or non-linear? You see, in this case, if I give 0 input to the system, the output is 0. In this case, if I give 0 input to the system, then the output is 1. In this case, if I give 0 input to the system, the output is 0. This one I can directly say is non-linear, because when I am giving 0 input to the system, the output is coming out to be 1. It can never be a linear system. So, directly I can say that this is a non-linear system. However, notice there is a cube term in the input here. So, this also is a non-linear system. However, when I gave input 0 to it, the output also came out to be 0. So, for a non-linear system also, it may happen that if you give 0 input, the output may be 0. That does not make it a linear system. But if a system is linear, then the input 0 must give you output 0. But if it is non-linear, there is no guarantee. 0 may give you 0, 0 might not give you 0 also. There is no guarantee for that. So, a necessary condition, a quick check whether a system is linear or non-linear is give 0 input to it and check whether the output is 0. If the output is 0, then you have to see, if you give 0 input to the system and the output is 0, then you have to go ahead and check all the superposition principle, whether it follows or not. Okay, then only you can claim that okay, the system is linear. But if you give input 0 and the output become non-zero, you can guarantee, you can directly at that step itself you can say that the system is non-linear. Okay. So, I will end this part here itself, and then we will take it up from this point in the next lecture. Thank you.